Welcome. Thanks a lot for joining the session. My name is Arif. I'm a developer with ThoughtWorks, and I came here from Germany, where I'm serving as the head of AI for ThoughtWorks Germany. And today I want to talk about the challenges of applying continuous delivery to machine learning applications. Maybe as a quick raise of hands, how many of you are developers? Okay, I think there was almost every single one. So I guess we do not have any data scientists in the room, right? We do. Fantastic. So I'm a developer myself. I'm not a data scientist, but this is a topic that fascinates me quite a bit. So before I go into the topic, let me say a few very quick words about ThoughtWorks. Who of you has heard of ThoughtWorks? Few of you are nice. So ThoughtWorks at its core is an IT consultancy. We are quite a bit smaller than the big IT consultancies, but we are a truly global company with offices in 14 countries, and we have a lovely office just 10 minutes down the road here. But for instance, I'm from the Berlin office in Germany, and one of the things that I believe makes us stand out a little bit is that we strongly believe in the power of diversity and that we can actually make the world a better place through what we do in our daily work. And then the other thing that we strongly believe in is open knowledge. And this is why ThoughtWorkers are very active in terms of conference speaking, like here, but also in terms of writing books. So ThoughtWorkers have actually been among the first to write about lean, about agile, about microservices, but also about continuous delivery, what is today's topic here. And another publication that we publish about 2 times a year is the ThoughtWorks Technology Radar. How many of you have heard or read the Tech Radar? Okay, not that many. So the Technology Radar is basically a state of the industry report. So similar to what maybe Gartner or other companies publish regularly. But what is special about the ThoughtWorks Technology Radar is that we only allow ourselves to put in techniques, technologies, frameworks, etc. into that radar that we have actually used on projects and with clients. So for instance, if there is a new technology or new programming language that we really like, but that we couldn't convince a client to actually use it, we don't allow ourselves to put it into the radar, because then we don't feel like we have actually seen it in the wild and know whether it's really good for production. And one of the topics that made it into the last edition of the Tech Radar is continuous delivery for machine learning, which is the topic of today's talk. Also, we just published an article on Martin Fowler's blog that goes quite a bit into detail about that topic. Do you all know, or do you read Martin Fowler's blog? Do you know Martin Fowler? Okay, a few more than who knows ThoughtWorks, I guess. So we talked and we wrote and published things about this topic quite a bit during the last 6 to 12 months. But actually the topic is not really that new. And for me personally, it all started almost 5 years ago already, in the beginning of 2015. And at that time, that was actually the time I joined ThoughtWorks. And that was the first project I got on as a developer for ThoughtWorks. And that was with AutoScout, where we were asked to help them rebuild their entire platform. So AutoScout is a European company. I don't know, here in Australia, what is the most popular platform when you want to sell a car online? Car sales, right? Yeah, that's what I guessed. So that is basically what AutoScout is in Europe. And what we were asked at the time when we came there was to help AutoScout to build a free price estimation product where users could get an idea what their used car is still worth. And so here's how how the user interface looks today, but it was very similar back then. You basically put in the make and the model of the car and the first year of registration, as well as the mileage, because it's about used cars, and then you just get a rough estimation what the car is still worth. I think today this is a fairly typical application of machine learning. Back in 2015, I think there were not that many applications where machine learning was really put into the hands of end users, so to say. So this was quite exciting to build that. And also there were not that many cases back then for user-facing applications built that way. So when we started building this, the situation looked a little bit like this. So there was the team of developers, and I was one of them, and we were meant to build the web application, the user interface, and so on. And then down here there was another team, the team of the data scientists, and they were meant to build the prediction model, which we, the developers, were then to integrate in the web application. And in between us, there was literally a wall, because we were sitting on 2 different floors. And then the data scientists, they would provide us with an initial version of the prediction model. The prediction model happened to be decision tree based, so that's why you see a tree here, and they were using R at the time. And then we, in the developer team, we integrated this prediction model in the application, and then provided feedback to the data scientist how the model is working in the application, and how it's doing. And overall, this feedback cycle here in the beginning was actually awfully slow. So we got a version of the prediction model, then certain things didn't work the way we wanted, and then we would give that feedback to the data scientist team, and it would take sometimes days until we get a new version, and then something was misunderstood and it was tricky to integrate again. So this was really, really slow and didn't feel very good. And this probably reminds you very much of the problem between developers and operations, which DevOps is all about to solve, right? To bring those things together and actually get rid of this throw over the wall attitude. And also, overall, we felt like from the developer perspective, we felt there was little empathy from the data scientist side. So basically, quite often the prediction model, a new version, would break the application because the interface had changed, and probably the data scientist felt the similar way that we as the developers, we could not really relate to their problems. So then, therefore, we wanted to apply a DevOps mindset here. And actually, one of the first things that we did was to bring those teams closer together and get rid of this wall, so to say, by actually bringing those 2 teams into the same room on the same table, and work really closely together and build one cross-functional team out of this. And this was probably the most important thing, and we did things like pairing between developers and data scientists, and have given other talks about this topic alone. But then, of course, there's one side of applying DevOps, and then the other side is continuous delivery. So we believe that continuous delivery is really one of the most important practices in DevOps, or in a DevOps culture. And generally in ThoughtWorks, we pretty much do continuous delivery on every single project, right? So it generally felt very natural to also apply it here in this case. And of course, at the core of continuous delivery, there is the build pipeline. And so this is how you can imagine basically the setup that we built here. So there's one pipeline for building the prediction model, which in the first stage pulls in the data from some base data source, does the feature extraction and the model training, and then as the artifact out of this stage we get the trained model. And then usually this trained model needs to be converted or wrapped or containerized into some kind of more interoperable model that is ready to be pulled into a serving layer and ready to be served. And so in the end, this is the final artifact of this pipeline. And then there is another pipeline, which is the web application pipeline, and this obviously contains the code of the web application and then builds this, and the main artifact here is the web application jar, and that gets deployed on a cloud server. And when deploying this then pulls in the latest version of the prediction model. And those two pipelines, they are coupled. So whenever a new or change is made to the web application, we make sure it always pulls in the latest prediction model. But also importantly, whenever there's a change made to the data science code or the model is retrained, this should trigger the prediction model pipeline and then actually also trigger the web application pipeline to pull in the newest model. And basically the final goal here where we wanted to get, because this is the state where we always want to get with continuous delivery, was that a data scientist would push a change, could even be a minor one, and then this would trigger a retraining of the model, and there would be enough automatic quality gates that this new prediction model would automatically go all the way into production and into the hands of users. But actually implementing this in a rigorous way was quite a bit harder than we anticipated, and also it was quite hard to convince the data scientists of adopting this approach as is. And there are several reasons for this. So here are a few of the challenges that we were faced with. How to version control training data. Training data is usually thousands of files, very large, so very different to version control than source code. Also, the training data is large, and also the prediction models are actually too large to put them into Git, because this is not what Git is made for. So you need to link to some external storage. Then another issue that we had was that a model retraining would initially slow down the entire continuous delivery server, because of course it's quite a different workload to build a web application source code or to retrain a prediction model. Then we found that the data scientists, they actually wanted to evaluate quite often several solutions at the same time, whereas we from the developer side were usually propagating a trunk-based development with few branches, so that was also a bit of a clash. And then to make things even worse, data scientists, they want to use analytics notebooks, right, like Jupyter and stuff, which is great for doing data science, but which is very hard to version control, or at least it's fairly ugly. And then how to actually unit test data science code that is tied to changing data. That is also not as simple as just writing unit tests or tests in general for general software development code. And then finally, how to prevent behavior changes of the model to break the application. So those were a lot of challenges that we were faced with at the time. So what are the reasons why it's so hard to apply continuous delivery to machine learning applications? because we were surprised, because yeah, as I said, we do this on pretty much every project for quite a few years now, and so yeah, we thought we were really used to do this. And I believe there are two main reasons for this to be fairly hard. The one reason is that there are different workflows. So as developers, I think we think that our workflow is not very linear and very creative and stuff, but when you actually look at it, it usually looks like this kind of, there is a master branch, sometimes we branch out a little bit, but then it gets into the master branch fairly quickly, and kind of overall it is fairly clear where we want to go, or at least with every step we know quite well what the next goal is and what we want to achieve. With data scientists, it's quite different. The typical data scientist workflow is branching out far more. So data scientists, they try out many things simultaneously and then just select one of all those things. So it's not even clear in the beginning which would be the route to go forward with. So there's much more hypothesis-driven development in this. So for instance, they may want to change the hyperparameters of the model, like here this change max depth of the decision tree, for instance, or they want to try out a different algorithm, like random forest here. So I think this clash of, or this difference in workflows alone makes it quite tricky to kind of cater both groups with the same tool set, or at least with the same approach to using those tools. And then for the other reason, let's have a look what continuous delivery actually means. And this is from the book from Jez Humble and Dave Farley. So continuous delivery is the ability to get changes of all types, including new features, configuration changes, bug fixes, and experiments into production or into the hands of users safely and quickly in a sustainable way. So this says changes of all types, including experiments. And this is exactly what this is about. And I would say this is kind of the second reason which makes it hard. There are actually much more types of change that need to be managed. So we have quite a lot of experience in managing changes of code, and sometimes we have other artifacts like assets or so that need to be managed as well. But here this is really, there are just more dimensions, because we also have to manage data, the training data, and this in itself again has multiple dimensions. So not only does the shape of the data change, like the schema, but also the sampling changes, because you want to always accurately reflect with the training data how reality looks currently, right? And reality changes, so you need to change that. And then there is the prediction model, and the prediction model contains kind of the code to build the prediction model, but also hyperparameters, or the parameters that are created when training the model. And then of course we have the software code as we're used to it. But this alone kind of creates much more complexity here to manage all those different types of changes. So a setup for continuous delivery for machine learning therefore actually needs to integrate all those artifacts, and also needs to cater for different pipelines. So this actually came out of many discussions where we were talking about pipelines a lot, and at some point we realized we're talking at least about 3 different kinds of pipelines. So one pipeline is the data pipeline, right? So the data pipeline, it pulls in data from the actual source systems and prepares it or makes it available in such a way that it can actually be used for the machine learning application. And that is usually what data engineers do, but sometimes also data scientists if there are no data engineers. And then the second type of pipeline is the machine learning pipeline. So the machine learning pipeline pulls in the data that has been provided by the data pipeline, and then in addition to that, pulls in the data science code, the code to train the model, to parameterize the model, and so on. And the outcome of this pipeline is the trained prediction model, or generally a machine learning model. And then finally, there's the deployment pipeline as we know it. And this deployment pipeline in this case here now pulls in the prediction model, that is the output of the machine learning pipeline, and additionally pulls in the application code. And then all this together gets deployed to production. So all those three pipelines actually need to be put together, and a setup for really keeping your AI applications in production needs to accommodate for all those different pipelines. And also it needs to support all those different stages. So let's have a look how this all can fit together and what the different stages are. So as the very first thing, there needs to be discoverable and accessible data. Otherwise you can't do anything. And this is kind of the job of having a good data architecture, data governance, a data lake or a data mesh to provide that. And then for the application itself, the first phase here is the data science or the model building stage. And that stage is pulling in training data, and it creates a model with parameters, or it pulls in parameters for that model, and also source code for training that model. And then the second stage is actually the model evaluation. And the data scientists in the room, of course, know this, that you need to, at least in supervised learning, that you need to clearly separate validation data from training data, so that your that there is no overfitting to your model. So this is the second stage here, where you actually test your trained model, and usually you also calculate the accuracy, so how good it is, how successful the training is. So this is what you do in this phase with the test data. But then afterwards, you usually need to productionize the model. So you usually cannot just take it as is into production. I guess in some cases you transform this, sometimes you wrap it into a different format. What you definitely should not do is manually translate it into some other version, but we still see it happening here and there. And these days, quite often it's containerized, so basically put into a model service that is then the main artifact here. But this is quite a crucial step to productionize the model. And then there actually needs to be integration testing. So that means we take the same test data that was used for the model evaluation and kind of double check whether the integration in the production environment was actually successful. So we test the whole setup again with the same data and make sure that it's really coming up with the same results. And this is quite a crucial step. So in the projects that I've been part of, this is usually where the issue is happening, of the integration between the model and the production environment. And then if all those quality gates until there, they get green, then this all gets deployed together. And then after deployment, you want to monitor the behavior of the whole application, of the whole system in the wild. And ultimately, from this monitoring, you actually get new data. That is the data that is produced by users using the system. And this is then actually kind of closing the whole cycle, where all the data goes back, and this data then, or parts of this data, serve as new training data. So for instance, in the case of the price estimation for used cars, users would actually get an estimation of what the car is still worth, but maybe they would actually deviate from the recommendation and they put the car on the platform for a different price. And then we would use this data again to retrain the model and adapt it to the current market situation. So this is the overall overall cycle, and this is what we really want to automate and kind of accelerate over time. So what do we need actually technology-wise to make this all happen and to build this? So first, I mentioned it before, we need discoverable and accessible data, so the data infrastructure. Then we need version control and artifact repositories for all the different types of artifacts that we're dealing with here. Then we need a continuous delivery orchestration tool to combine all those different types of pipelines. Then we need the infrastructure for kind of multiple environments and experiments to allow for kind of this simultaneous experimentation and run multiple things in parallel here. Then we need tools for model performance assessment to actually find out whether the model is good enough, and also whether the quality is not deteriorating over time. And then finally, we want to monitor and observe the whole system in the wild. So really see how it's performing while it's live. And you can now actually implement this stack with many different technologies, and ThoughtWorks in particular, or at ThoughtWorks, we are very technology agnostic. So we really choose the tool that is best, the best tool for the job, and we rarely do any partnerships. So this is kind of just one example technology stack that we use to build this. So here in this case, we used Google Cloud Storage as the data infrastructure. Then for version control, we used Git together with DVC. Who in the room has heard of DVC? Again, no one. Doesn't surprise me that much. It's a fairly young tool, and it's a small tool. It's abbreviation for Data Science Version Control, and it's just a small command line tool. And we like it because it is a small command line tool that you can integrate nicely with existing continuous delivery tools. And that kind of bridges a little bit the gap between those two different workflows that I talked about earlier. And I will actually show you it a little bit in action in a couple of minutes. And then for continuous delivery orchestration, we use GoCD. GoCD is a continuous delivery tool that has been built by ThoughtWorks and is maintained by ThoughtWorks, but it is open source, and we do use a lot of other continuous delivery tools as well. Here in this case, we thought that it would be the weapon of choice, so to say, because it is very good at this combination of different pipelines. And then for the infrastructure, we used Google Cloud Compute in this case, with Docker, of course, these days. Then for model performance assessment, we have been using MLflow lately. And interestingly, there are not many tools around these days for model performance assessment. At least that is our impression. And MLflow can actually do quite a few more things. But this is what we use MLflow for. And then for monitoring and observability, we basically use kind of a standard stack with Elasticsearch, FluentD, and Kibana. So now I actually want to do a little demo. I'm kind of showing something live here, but I do not have the time to kind of go through the entire stack. So I will concentrate on this piece here for version control and the continuous delivery orchestration mainly. And the demo basically that we look into, you will see kind of the pipeline setup that is created in GoCD, and kind of a little example application. And then I just want to go one time through this continuous delivery cycle where you push a change and then the change is actually tested, in this case change in the data science code, and then depending on whether it passes the quality gates, it is pushed to production. So let me see. So here we see, I can probably make that a bit larger. There we go. So here we see the two delivery pipelines, and those are the two pipelines that I was talking about before. Keep in mind, this is a very simplified example, right? So this is an example used for a workshop that we ran, or that we run quite often these days, to kind of show how all of this is working, but it's very simplified. In reality, things get quite a bit more complex with far more pipelines. So this is kind of the application pipeline, the web application pipeline, and this is the machine learning pipeline. And then what is interesting is that GoCD has this value stream map view, where you can actually see the dependencies between the different pipelines. So you see here that both pipelines, the machine learning pipeline and the application or web application pipeline, depend on the source code in Git. But the web application pipeline, in addition, depends on the output of the machine learning pipeline, which is the prediction model here. So this is kind of the very basic setup for this. And then here we actually see the very simple application that we're deploying to production with this. In this example application, we're implementing a sales forecast. So basically, this came out of a work that we did for Ecuadorian supermarket chain, and then we kind of simplified the example drastically. So this is kind of to pick a date and then kind of ask how many items of milk will be sold on that particular day, 30, clearly. So this is the application here that we will redeploy to production. And now those pipelines here, they are both connected to my personal fork of the repository, of the workshop repository actually. So you can see that here. So that is actually a fork of a public repository. You can actually have a look at it. It's called Continuous Intelligence Workshop, and it contains very detailed and easy to follow instructions, also to go through something like this. And what I'm now going to do is actually to go into the source code here and make a little change in the data science code, or in the model training code. And actually my goal here is to intentionally make the pipeline red. So basically what I'm doing here is I'm trying out a different algorithm basically. So I switch from random forest to a basic decision tree algorithm, and then I push that directly to the repository here. So now what we should see here is that within the next 30 seconds, yeah, there we see, both pipelines are triggered. The reason for this, that both pipelines are triggered, is that kind of we saw before that both pipelines depend on the source code, and in this case we didn't bother to separate it by subfolders, so technically you could also say those files belong to the setup of the machine learning code, and those subfolders belong to the web application code. So then we would kind of avoid the unnecessary triggering of the application pipeline right now, and only that one would run. And so now this one is running here, and we can follow that a little bit. And we see, okay, and now we see kind of this typical data science or machine learning training workflow happening, where first the training data is split into training and validation data, and then it gets trained and evaluated. And while this is happening, I can actually look a little bit in how this works. So when we go here into the details of this stage, it all takes a while. So here we have a kind of a job that is called train, test, and publish, train, evaluate, and publish. And here we actually use this little tool, DVC, that I talked about before. And I mentioned before that DVC is bridging this gap between the different workflows. So DVC is very simple, but with DVC you can basically record data science workflows and the different dependencies. And then you can use the command DVC repro, which means reproduce, and then reproduce the model. And it will actually check which dependencies of building the model have changed, and will kind of rerun the process back as much as necessary. And this is the only thing that we run in here. So we basically really just run this little command line tool here to reproduce the model, and it automatically detected that one of the relevant source code files changed, so it needs to rerun this. And then we just do a very simple test to check for the accuracy. And so let's see. By now it actually got red, and a red pipeline is actually a very good thing, because it usually means that it prevented something bad to go live. So that's what you want. So when we go in here, we just see that basically the test that failed is that we want to have at least an kind of 80% error rate, and it was or less than 80% error rate, and it was higher than that, and therefore it was actually prevented from going to production. And what we then see here is that because this failed, that this here was not re-triggered. And now I can very quickly make another change here. So I can just change this quickly back to random forest. There we go. And now we will actually see that this pipeline is going to be re-triggered, will be green, and then, I mean, first we will see both be triggered because of the reason I mentioned before, but then after this becomes green, this will become yellow to be, because it's re-triggered by the redeployment or retraining of the model. And yeah, so we see currently both of those being re-triggered, and then afterwards we'll see only one of them. So this gives us some time to also look into this one. So here we see that in the build stage, that here we use DVC as well. So it's a bit hidden here on this side. So we say DVC pull, and this will actually pull in the newest prediction model from some cloud storage. So DVC is also used to link between Git and cloud storage. In this case, we use Google Cloud. So it basically just manages files that link to external storage, similarly to how Git LFS is doing, just that it integrates it a bit more nicely in this data science workflow. So this is exactly what is pulling this in here. And we see a similar command, dvc push, being applied in the machine learning pipeline. And so let's have a look. Yeah, this actually takes a few more seconds because actually the random forest training takes a bit longer. So we can have a look here. So if I open this again, we see here this dvc push happening. So basically it reproduces the model, then tests the performance of the model, and only if the performance is good, it will push the model to an external storage from where it is pulled into the web application. So go. Okay, it's still not finished, but I guess you believe me that this is going to become green in a couple of seconds, and then it's going to re-trigger that one here to pull in the latest prediction model and redeploy the application. So quickly switching back to the slides to kind of wrap this up. And I want to wrap this up by talking a little bit about that applying continuous delivery to machine learning is a nice, or a very interesting and challenging task. And I find it very fascinating to solve those puzzles and to come up with the right technology to solve this. But overall, it actually needs to fit into what we call the continuous intelligence cycle. And this, to us, continuous intelligence is a capability of a business. And that's kind of the larger narrative into which this needs to fit. And we must never forget that it's actually about creating value and not about solving technical puzzles. So this continuous intelligence cycle is a cycle where we first acquire data, and so there needs to be the right infrastructure for that. But then actually data in itself has not much value, so we need to get information out of this data. So we need to curate it, need to clean it, need to featureize it. But even the information itself has not much value to it, because we need to get insights from this information. So understanding needs to be generated out of this. And this is, for instance, what the model represents. Then this needs to productionized in order to drive decisions. So also the insights are not of much value if they do not drive decisions. And those decisions, they can be manually, they can kind of the model can inform someone who is doing some decisions as a person, or they can actually drive automatic decisions. This is when we really bring AI applications entirely to production into the hands of users. And then, important, this decision needs to drive an action in the real world again. So basically, for instance, someone selling their car. And only then we really create value when this whole loop closes. And this action in the end changes the real world. And because the data that we acquire in the first state is only a sampling of the real world, the loop closes here, and this is really what we want to achieve. And basically our goal, and we feel that applying continuous delivery is only one piece to get to that goal, is to accelerate this cycle of continuous intelligence and make it ever quicker and close that loop here. And with that, thanks a lot, and I'm happy to take a couple of questions. Yeah, I still have a couple of minutes. Any questions? Yeah. Yeah, So just to repeat the question, it's about how to package a model for production, and I'm afraid there is not one solution really that we figure out yet. It depends quite a lot on the case. So I have seen models being transformed or exported in some kind of intermediate format, like the PMML, like a markup language, so that the model can then be served in a generic serving layer. What I have to admit, what I see these days much more often is that we actually package the model as a service, so to say, so that basically we create a very simple prediction service, a layer around the model, and then deploy this as a container entirely, and then put it into a container registry, and from there, this is where we pull it. There are a lot of other things for this project that I mentioned initially. We used H2O and then exported it to Java files and pulled in the jar file then. I think I've seen many different ones, and I feel that currently we're leaning towards wrapping this into a service with a very thin layer of a web service then serving the predictions. In a certain way, yes. So this was what I was talking about before. We favor to bring data scientists and software developers much closer to each other. And that means that we also try to make them pair and do pair programming. It's not always the right thing to do, but that also means that ideally a data scientist and a software engineer sit together and then create that simple layer, for instance. And we find that very fruitful because then also the developer learns a bit about how the model is working, and so there are less silos and less bottlenecks if someone is not there. And I mean, generally also we see that often the data scientists are the even scarcer resource than developers. So that means that often the data scientist comes into a team for a while to develop or help developing the application or the initial version. And then ideally as much general knowledge about how this is working is transferred to the developers. So this is how we integrate usually them. And to your question, whether we upskill the data scientists, we feel that naturally this way also then some knowledge gets over to the data scientists how to deploy applications. And this on the other hand creates more empathy of how to build a system that actually needs to be live and create understanding what needs to be done to do those things. So we have one in the front and one or two in the back.
Thanks for the preso. So I understand that that was out of the scope of your presentation, but you touched on one of the challenges that you had, and that was versioning of the data, the training data. Would you be able to comment a bit more on how you version the data? For example, if you have a data field change and that means there is a change in the training data, how would you manage that? Would you create a copy of the whole data and store it as a blob, or how would you do it?
Yeah, pretty much. So to come up with a good kind of smart solution for data versioning is a very tricky topic, and a colleague of mine, Emily Gorchansky, has written a whole blog post about data versioning. What we do in this case also that we showed, that I showed to you here with DVC, is a very simple version where basically we do not version control the data itself, but only manage a pointer to the data set, and then just the pointer changes, and we need to point to a new version of the data set, and this is what is recognized by the system. It's a very simple way to approach this, or simple basic way, so it cannot really understand or automatically detect changes like data fields. Which means also everyone working on the project, including a data scientist, they need to understand how this is working, which means they need to understand that they need to create a new data set, or at least a new bucket or whatever, when there is new data, so that the system can recognize this. But this is, it's to come up with a smart solution is still out. I think there were at least one back there and one more here in the front.
I noticed in the diagram that you have a stage where after the model building process, you have an evaluation stage as well. So at the moment, me as a developer, I was told to validate the model just manually, but I have very little knowledge about AI. So how do you automate that process?
That is really mostly about automatic validation in terms of checking whether certain accuracy thresholds are met. I think that's the typical thing that you do there. And this is actually usually just the normal work of data scientists. This is really what data scientists always do. They have an evaluation stage that they implement that creates a score usually. So creating that test stage there is often just to check for the score. As always, with fixed thresholds, this can be tricky because you need to adapt them, but that's really what it's about. So this is not that complex. Go ahead.
Sorry to interrupt. Just to clarify on that question, I'm super new to AI. So you would have a final data set of like, say you use the cats and dogs images, the typical example. You would have a list of cat images and dog images, and then you would have expected output, and you would run that through your end model. And if you got a certain number of like, yes, that's a cat, no, that's a dog, then test passed.
Yes.
Yeah.
So it's, I mean, we're talking about supervised learning here. Supervised learning means we know what the right answer is, and therefore we can just create an error score and say 70% of the answers were what we expected, and then we can just define what is good enough. I think there was definitely one question here in the front. I don't know whether that's still open.
I just wanted to follow up the comments before about getting the teams, or the developer and the data scientist, to work together. We currently have a team that work together, but they're very reluctant to sit with each other and work together. Do you have any content or blogs that I can point them at and say it actually works?
Yeah, so I mean, I've written about this, especially also about this case with AutoScout. But to be honest, it's not easy. I think the most important thing is probably to acknowledge that there are different workflows and different ways of working and different skill sets. But to really make clear again and again that it's beneficial to work closely together, but it will actually slow you down. I mean, this is, as with any kind of different skill set, bringing together, be it like an operations guy with someone with a developer, or putting together a front end and a back end developer, you will always feel that this is uncomfortable, mostly actually for the one who is better at the topic at hand, because they feel slowed down. So I guess this is really kind of a bit of a leadership thing to really make clear that this slowdown is okay, because it will actually enable the entire team to be more sustainable and be less dependent on a single person. But yeah, I guess if there's a culture of constant pressure for bringing things out, then it can feel uncomfortable to be in those pairs that slow you down. I guess if the environment is right, I would say that it can be very good to teach certain things to the other partner of the pair that doesn't know that many things about it. But yeah, the situation needs to be right. It needs to be right. Yeah, but that's definitely not easy. But it's similar in all disciplines.
Yeah, you talk about the continuous monitoring. So, say for the model built after 3 months, 5,000 more cars sold. So those information can be fed back to the model to retrain the model. How do you make this automate?
In that particular case, I think there are two ways to go about this. The one is just the implicit way, so to say. It's basically, we originally draw the training data from the production data, basically, and just a couple of months later there will be different production data, right? So just the new cars sold will add to the production data, and therefore we pull in different data, so it's really just about scheduling a retraining. Another way would be to kind of schedule a retraining when we feel that the quality deteriorates, or that we see that the users, for instance, will trust the model less and less. But generally what we try to achieve with this is that a model can be retrained and brought to production several times a day, so that we're really not thinking too much about this and just retrain it very often. Another way to solve those things is just to kind of build a Lambda architecture where you have kind of a batch layer, which is about the model being retrained not that often because it takes long, and then have a second layer in front of this, which adds live information and maybe filters out things. So I've seen things like this with recommender systems, where we only retrain the recommender model once per night, but for instance filter out the recommendations that a user has already clicked on, and this is just a very simple layer in between the user-facing application and the prediction service, which just checks whether the kind of retrieves the outcome of the prediction model, and then just filters out the things that have already been presented to the user. All right. Then one last question.
In your monitoring stage, I noticed that you use Elasticsearch and Kibana. Can you just illustrate what you actually monitor?
So this is actually kind of this stack with FluentD, Elasticsearch, and Kibana is really just a typical monitoring stack these days, I would say. What we do there is typically monitor business events. So we try to implement the application so that it emits business events, something like a car put on the platform, or price estimation happened, and then always with a certain data attached to it. And then this data basically ends up in Elasticsearch, which makes it easy to query. And then you can create automatic dashboards and can filter for certain things. So this setup is very good to kind of monitor what is happening and maybe see trends. Or, I mean, it's actually also very good for debugging, but that's a different story. So you can basically see a log of what happened. Great. Then, thank you very much. And of course, I will be staying here.